From the Library of Congress in Washington, D.C.
Good morning, afternoon. 11:30 is always afternoon, morning. My name is Jennifer Harpster. I am a research and reference specialist here at the Library of Congress for the Science, Technology, and Business Division. And I'd like to welcome you to today's program, Icy Volcanism in the Outer Solar System. This program is part of a 2015 series of lectures that's presented through a partnership between our division and NASA's Goddard Space Flight Center. And I'm very happy to report that this is the 9th year that the library has been partnering with Goddard. It is my pleasure to introduce today's speaker, Dr. Lynnae Quick, who is a research scientist at Goddard's Planetary Geodynamics Laboratory. Dr. Quick received her undergraduate degree in physics at North Carolina Agriculture and Technical State University, a master's degree in physics at Catholic University, and a master's and a doctorate, way to go, in earth and planetary sciences at Johns Hopkins. In addition to her work at Goddard, Dr. Quick does outreach to inspire girls into STEM careers. She has been featured on the Women in Planetary Science blog, which I have to plug for the library because we're archiving the Women in Science Planetary Science blog for our web archive project. And she's also been involved with the Carnegie Science Center STEM initiative called Canteen program that inspires girls into science careers. As you will discover, Dr. Quick has a really exciting and I think dreamy job that includes volcanoes, icy moons, and distant worlds. She uses analytical methods to model volcanic and cryovolcanic processes on the terrestrial planets and the moons of the outer solar system, with a particular emphasis on Jupiter's moon Europa. Her other research projects focus on Venus volcanism, stability of a subsurface ocean on Triton, and that's Triton, which is Neptune's moon, not Titan, which is Saturn's moon, and the Europa imaging system. So let's get to learning about icy volcanoes in the outer solar system, and join me in welcoming Dr. Lynnae Quick to the Library of Congress.
Okay, good morning. I'm very happy to be here. I'm used to walking around a little bit as I'm talking, so please bear with me. Thank you so much for the introduction. And so this is work that I've done in collaboration with Lori Glaze at NASA Goddard, Steve Beloga at Proximity Research, and Bruce Marsh at Johns Hopkins University. And so you can see here to my right, your left. So this is an artist's conception of an icy volcano or of a cryovolcano and erupting on an icy moon. And then next to it, we see a picture of Jupiter's moon Europa, which I have to say is my favorite moon in the outer solar system. So we'll talk about this. Before we go there, these pictures were floating around Facebook actually last week, and I got very excited. These are two images from the Agricultural and Mechanical College in Greensboro, North Carolina, now North Carolina Agricultural and Technical State University, in 1899. And so this is the school where I received my bachelor's degree from. And then you see one image, students in a biological laboratory, and as our motto, the motto of our school that goes with our seal is minds and hands. It's an agricultural school, so you have to teach them something that has to do with agriculture and farming. So there they are in their Sunday best, learning how to churn butter. And this young lady here looks like she could not, she looks like she could not be any less happy in her Sunday best learning how to churn butter. When I was at A&T, we still had biological laboratory. We have a farm, nice cows and pigs and all of those things, but I can say I never took a butter churning class. So she's hopefully she's thinking about planets. So again, these images are ones that you all have at the Library of Congress, and I was glad to see them. I'm sure they would be glad that I'm here. So let's get into talking about cryovolcanism. So here's an outline of my talk. You're going to see that there are lots of nice, pretty pictures here. This again is an artist's conception of a surface of an icy body in the solar system. First, I'm going to talk about volcanism in our solar system. What are the different types? Give you an introduction to cryovolcanism. What is it? Where do we find it? Then we'll talk about Europa, its physical properties and evidence for cryovolcanism there, or icy volcanism. We'll talk about the compositions of these lavas. I'll talk briefly about a model that I've developed with some of my colleagues. We'll talk about the implications of that model. Then we'll touch on NASA's Europa mission. That's very exciting. And then just leave you with a few lasting words on the importance of icy moons. So there's the outline. So let's talk about the types of volcanism in our solar system. What you all are used to, what we see on Earth, is silicic volcanism. And again, that's volcanism that we see on the Earth. It's happened on Earth's moon, on the planet Mars, the planet Venus, also on Jupiter's moon Io. There's lots of silicic volcanism happening even now. And so this is where the lava or the magma is molten rock. And so I'm going to use lava and magma interchangeably. So both of them are the same material. It's just magma is this molten rock when it's in the subsurface. After it erupts onto the surface, that's lava, same material. And so then we have silicic volcanism, which is what we're used to on Earth and other terrestrial bodies, and cryovolcanism, which is what I'm going to talk about today. And this occurs on the icy moons of Saturn and Jupiter. It may occur on some of the Kuiper belt objects like Pluto and Charon, and possibly on hydrous asteroids like the asteroid Ceres, and again, cryolava or cryomagma. I'll be using that interchangeably. And so usually these are just fluids that are aqueous solutions. It can be pure water. You can have water mixed with salts and mineral acids, ice crystals, gas bubbles, water vapor, carbon dioxide, things like that. So we'll talk about that. So let's back up a little bit and talk about silicic volcanism just for one more slide. There are two types of lava that we're familiar with on Earth. There's the mafic lava, which is rich in iron and magnesium. It has an eruption temperature greater than 900 degrees Celsius, and this type of lava, basalt, is a mafic lava. And if you've ever seen any eruptions in Hawaii or pictures of eruptions in Hawaii, you know that this type of lava is very quiet. It's very effusive. It likes to erupt and just quietly flow along the ground. There's no explosive eruption. There's not much gas or much volatiles in these eruptions. And then we have felsic lavas. And these lavas, such as rhyolite and dacite, they're rich in aluminum and potassium and other elements. They have slightly smaller eruption temperatures than mafic lava, and they're full of gases and volatiles. And these are very high viscosity, explosive eruptions. We see here on this slide Krakatoa in Indonesia, which is erupting. There's a lot of felsic lava here. If you think about Mount St. Helens, that's a lot of felsic lava. So mafic lava, quiet, effusive, flowing, gentle, everything's fine. Felsic lava, you want to run. It's explosive. It's very violent. And so when we think about cryovolcanism, we also have this kind of effusive quiescent lava that just flows nicely, and we also have explosive cryovolcanism that occurs. And so explosive cryovolcanism is kind of what you see on this artist's conception. It's geyser-like eruptions where you have ice particles, water vapor, maybe carbon dioxide. And again, when I say ice particles, a lot of times it's water ice, but as you move out further and further into the outer solar system, you might have nitrogen ice just erupting very violently. Think about Old Faithful, but very Old Faithful in Yellowstone, but very big and very cold. And so you also have effusive eruptions, which again are just these fluids. You may have ammonia as a liquid once you get out to the outer solar system because it's so cold and it's flowing onto the surface very quiescently. And so one thing to keep in mind is that these eruptions are occurring on bodies that are extremely frigid. So their surface temperatures are between negative 233 and negative 173 degrees Celsius. So these are cold moons and cold objects. And if you think about at that temperature, ice is so cold that it behaves the way bedrock behaves on Earth. So there's really some interesting stuff that happens there. And so you can see that the maximum eruption temperature of a cryolava, if you see here, is 0 degrees Celsius. Here, that's pretty cold. Water's, you know, it's freezing. Out there, that's hot. It's very, very hot. And so we already talked about where it occurs, and I'll talk about some of these bodies. And one thing to think about when we're talking about cryovolcanism is you can't always compare it apples to apples with volcanism on Earth. Cryovolcanism, in some sense, is a misnomer. Now, I'll tell you why. So we see on these images, I don't know, can you all see the little arrow from my cursor? Yes or no? It doesn't look like people can. Okay, all right. So we have on the top left, we have an effusive eruption. This is the quiet eruption, basaltic lava erupting from Mauna Loa in Hawaii. Then beside that, we have Mount St. Helens, an explosive eruption. Then on the bottom, the very first picture to your left is a fissure eruption, and this is also in Hawaii. And so these first three images that I've pointed you to, nobody would say these are not volcanic processes. You have volcanism going on. It's clear these are volcanic processes. But if you look at the kind of yellow tinged figure on the bottom in the center, this is a fumarole, where we have just steam coming up from Earth's surface, and then here's Old Faithful geyser. So nobody on Earth would say that this fumarole and this geyser is a is a volcano erupting. But because of these, when we get out into the outer solar system, all of these processes on this slide would be considered cryovolcanism simply because of the materials that these moons and these bodies are made of. They're made of ice, they're made of water, they're made of carbon dioxide. So any venting that you see from the surface, whether it looks like a geyser, whether it looks like something that's erupting from an icy volcano, we call that cryovolcanism. So we've talked about cryovolcanism, the differences between cryovolcanism and just the silicic volcanism that we see on Earth. So what was our first look at cryovolcanism in the outer solar system? Well, our first look was when Voyager 2 flew by Neptune's moon Triton, and this is the largest moon of Neptune. And you see Triton at the top here. I will say Triton is it's a sphere. The reason that it looks like this is because the camera, when it took the picture on the spacecraft, was not able to get a lot of the northern hemisphere, but I promise you it's not cut off like that. I have to say that I don't want anybody to think that, it's kind of, it's funky looking, but it's actually a sphere, and I like Triton. I have to say when I was much younger, it was one of my favorite moons because it's actually tinted pink, and I love pink. So we see that we have these, if you look at the bottom going from left to right, we see these walled plains units, and the first image on your left and the image in the middle, this is the exact same surface just from two different viewpoints. And what it looks like, these depressions are about 200 kilometers across, and there have been depressions, and we believe that ammonia lavas flowed into these depressions and filled these up and kind of made a smooth surface. The surface of Triton is negative 233 degrees Celsius, so having liquid ammonia there to flow can happen. And if you look at the bottom, the south pole of Triton here, and then you look at the image right below that, you can see these dark streaks. These are actually nitrogen geysers. And the Voyager team was so excited when they first saw these. So they're similar to Old Faithful, but erupting again cold. They're 8 kilometers above the surface, and so it's pretty cool. That was our first look at cryovolcanism, and so everybody was really excited. After these images were taken, people started looking at images from other moons that the Voyager spacecraft had looked at. If you remember, Voyager 1 and Voyager 2 did kind of a grand tour of the outer solar system and took these images of several different moons, and so anywhere that there was a smooth surface, people thought, oh my gosh, here's an icy moon, we don't see craters, there's a smooth surface, we don't see many depressions, there has to be cryovolcanism everywhere. And so people were excited. People looked more at those images. The Galileo spacecraft went to the Jupiter system, it was great. When we found out after a couple of years that cryovolcanism was not as widespread as people had assumed, and that was because we were looking at low resolution images at the time. And so as technology got better and we had more missions, then we sent Cassini to the Saturn system to look at Enceladus, and this is Enceladus here. Enceladus is a cute little moon, and again, the image is cut off. The one side of it is in shadow, but I promise you it is also a sphere. And so it's a moon of Saturn. It's a little warmer than Triton, negative 198 degrees Celsius on the surface. And we saw these spectacular things when we looked at them. We saw these geysers erupting from the South Pole. And these geysers are mostly water ice. There's some ammonia in there. There's evidence for rocky particles and salts. And these geysers they extend way out into space, up to 500 kilometers off the surface of tiny Enceladus. And this is really crazy because Enceladus is a moon it has a radius of 252 kilometers, which means it's about the size, it has a radius of about the size of Great Britain. So it's very, very small. But you have all of this going on. And if you look at the bottom of this image of Enceladus, you should see these kind of bluish in the South Pole, you see kind of these bluish lines. We call those the tiger stripes, and that's where these geysers are coming from. And so it's really exciting. We've also learned that these geysers actually feed ice to Saturn's E-ring, to one of Saturn's rings. So these particles are really moving. So that's great. We saw, we've seen Triton, we've seen Enceladus. What else? Well, then there's Titan. And Titan is not to be confused with Triton, of course. And so Titan is Saturn's largest moon. It's the only moon in our solar system with an appreciable atmosphere. It's very dynamic. There's lots of cool things going on there. And so there's been kind of speculative evidence for cryovolcanism on Titan. If we look at the first image at the bottom to your left, Ganesa Macula is there are three images. So the first one to your left, you see Ganesa Macula. And people got really excited when we first took these radar images, and people thought, oh my gosh, here is an icy volcanic dome or a cryovolcanic dome on the surface of Titan. And the reason being is because if you look to the image of the right of that, the image to the right of that is the Rusalka dome, and that is a volcanic dome made by very viscous lavas on the surface of the planet Venus. And people thought, oh my gosh, they look just alike, and there are even arrows here on Ganesa Macula on Titan showing what we thought were cryolava flows erupting from the top of that circular feature, which we thought was a vent. And so people were very excited about that. Then Cassini took more images, and we found out that this is actually, Ganesa Macula is not a cryovolcanic dome. It's actually a feature that's caused by tectonics. It looks like this because you have different movements in the crust and in the lithosphere. When you take images from different angles, you're actually able to see that this is not a cryovolcanic feature at all. So we thought, oh, that's really sad. No cryovolcanism on Titan. And so then in 2010 and 2013, we took some images of this region on the surface, Sotra Facula. And it appears bright in radar images. It has irregular terrain, which we now believe that Sotra Facula is a cryovolcano, and some of these white features that you see, this is to your far right, are cryolava flows. So that's great. We think there's cryovolcanism on Titan. We think Sotra Facula is it. People are still studying that. One thing that I will say is Titan has since it has such a thick, dense atmosphere, we wouldn't expect to see anything explosive, no geysers. We would expect to see just these thick, viscous lavas that kind of meander across the surface. So that's great. We've talked about Triton, Enceladus, Titan. What about Kuiper belt objects? And Pluto, poor little demoted Pluto, which was a planet when I was in elementary school. But it's, New Horizons. I don't know if you all heard about the New Horizons mission that's run out of Johns Hopkins Applied Physics Laboratory and NASA. And so we're getting back images from New Horizons as we speak, and they're still downloading data, and they're still analyzing it. And so this is a true color image of Pluto now, and that heart-shaped region is Tombaugh Regio, named after Clyde Tombaugh, who first discovered Pluto. And something that's really, really interesting, if we look at start looking at the picture to the right, if we zoom in on Tombaugh Regio, we see that there's a lot of smooth surfaces. And we did not expect that. We expected there to be a lot of impact craters and lots of depressions. So we didn't expect that smooth surface, and it's been theorized that the smooth surface may either be just ice flowing across the surface, just meandering, or the project scientist for New Horizons during the press conference said something that made me very happy. He said, cryovolcanism. Maybe geysers. We're still getting in data. And so if we look at this picture to the bottom left, you see these mountains, these little mountains and wrinkles and bumps and uplifts, and in between them the surface is very smooth. So that could be cryolava flows. And I will say that before New Horizons reached Pluto, we did have a workshop where we talked about what we thought we might see on Pluto. And Pluto was thought to be very similar to Neptune's moon Triton, where we first saw cryovolcanism. So a lot of the theories said there would be cryovolcanism on Pluto. So we see smooth surfaces. That makes us happy, but we're going to have to wait a little bit. And so then there's Pluto's moon Charon. And Charon is much more geologically complex than we thought it would be. And this is, again, is a new image from New Horizons. And one interesting thing about about Charon and other Kuiper belt objects such as Quasar, I don't know if you all have heard of that, is that telescopic observations from Earth reveal that there's crystalline ice on the surfaces of these bodies. Why do we care that there's crystalline ice? Well, these bodies don't have appreciable atmospheres. And so any ice that's on the surface of these bodies, we would think it would be amorphous. And by crystalline and amorphous, crystalline is just you have ice and all the molecules and the atoms are in this nice ordered structure. Amorphous ice is when it becomes disordered. So we expect to see disordered amorphous ice on the surfaces of these moons. On the surfaces of these bodies. And so telescopic observations show us that there's been crystalline ice on these bodies. Crystalline ice can't stay on these bodies for very long periods of time because they have no atmosphere. They're hit with different objects, comets, asteroids, even some particles from the sun streaming way out. So anytime you have crystalline ice on the surface of a body with no atmosphere that's this far out, that is a sign that something has replenished the ice on the surface and brought something new from the subsurface. So that was taken to be a sign of possible cryovolcanism on Charon and other Kuiper belt objects. Again, as this third bullet point says, New Horizons data is still coming in, and so we'll hopefully they'll find something that would make me very happy. And then now we're looking at water-rich asteroids. So this is the asteroid Ceres. It's the largest asteroid in our asteroid belt. It's a lot warmer than the other bodies that I've been talking about. It's a lot closer in. So it's a water-rich asteroid. It's the largest asteroid in the asteroid belt. And like I was saying, it's a little bit further in than some of the bodies we've been talking about. You can tell because it has a pretty warm surface temperature of negative 105 degrees Celsius, whereas Triton, we start out at negative 230. And so it's closer in. If we think about the order of the planets from the sun outward, we have Mercury, Venus, Earth, then we have Mars, then we have the asteroid belt. That's where we find Ceres, and everything else is farther out. So Ceres is pretty cool. It has this interesting, if you look at this picture on the bottom, it has this interesting internal structure. It has a rocky core from inside out, a rocky core, then there's a water ice layer, and then there's this thin dusty crust. And there's lots of clays and things like brucite on the surface of Ceres, and brucite is a mineral that has the formula MgOH2. And that's basically Malox. That's basically milk of magnesia. So you have this nice dusty milk of magnesia crust on Ceres. So it's pretty interesting, and you notice that there's a water ice layer. And when we say that things in the solar system have a water ice layer, that's always kind of tricky because that means that there's a chance for there to be water and ice, but we're not sure within that layer how much of it is water and how much of it is ice. So the thinking is that Ceres may have a subsurface ocean, which would be very cool if it does. Dawn just reached Ceres a couple of months ago, I think right before New Horizons reached Pluto. So we're still learning more. This is a new image up top of Ceres. And something that's interesting is that ESA, which is the European Space Agency, their Herschel Space Observatory actually observed water vapor being spewed out into space from two spots on Ceres. And this is just an artist's conception. This is not what they saw. No one actually saw this. And so they now believe that water vapor could have been due to cryovolcanoes or geysers just pumping water vapor out. And so that's an exciting place. We also see, if we look at the picture of Ceres, this is a real picture of Ceres up at the top to your left, there are two bright spots, and I don't know if everyone can see those, but those bright spots are either thought to be salts or ices. Either way, two of the theories are that they were bought up either by actually icy volcanoes or icy geysers. So either way, Ceres is very interesting. So we've talked about this, and is it almost 12? Okay. So we talked about this, and so now let's get to Europa, which is the moon that I did my dissertation on, my favorite moon in the outer solar system. And you can see that Europa has this opaque white surface, and that's the ice. And then you have these reddish brown regions, which we believe are salts. You have lots of these lines across the surface, and those lines, singular for those lines is Lynnae, plural for those lines is Lynnae. So there's a certain conference that I go to, and whenever I talk about Europa, someone always tweets, her name is Lynnae, and she's talking about Europa. There are lots of Lynnae. What a fitting name. So it's just maybe I was born to study Europa. Who knows? So let's talk about Europa from the inside out. You have a small iron core. You have a rocky layer or a rocky mantle, and then you have a water ice shell. But remember what I told you about water ice shells. Some part is ice, some part is water. We're never 100% sure which part is which. We can tell by looking at pictures of Europa that the outside of it is ice. That makes sense. The crust is ice because ice is less dense than water. You know that ice cubes float in water, so that makes sense that the ice would be at the top. Below it, we believe that from measurements by the Galileo spacecraft that there's an extensive ocean beneath it. And so this water ice layer is between 100 and 150 kilometers thick. And so we think that the ice layer at most is maybe, somewhere between 20 to 40 kilometers thick. So that's a lot of water. Europa actually has twice the amount of water that the Earth has. And if you look at this image at the bottom of Earth and then our moon and Europa, you see how much smaller Europa is than Earth. So to have that much water is just astounding. And so one thing that's interesting about Europa is it's about 90% ice and 10% rock. We call it an icy satellite, but really it's mostly rocky. And that's part of the reason that it has some of these dynamic processes that are so interesting. One of my professors at Johns Hopkins used to joke that Europa was really at 90% rock, was really a rocky body just masquerading as an icy body. But why do we call it an icy body? Because all of the geophysical processes and geological processes that we can see actually occur in the ice. And so it's a little bit smaller than our moon. We see the radius is about 1560 kilometers. Our own moon, the radius is about 1738 kilometers. And the surface is a chilly negative 173 degrees Celsius. You've seen these reddish brown marks on the surface. A lot of that comes from some of these surface species. We see carbon dioxide, carbon monoxide on the surface. We see sodium chloride, which that's regular old table salt, magnesium sulfate, just a sulfate salt, and also sulfuric acid hydrates. One thing that's really interesting about Europa is that it may be the only other body in the solar system in addition to Earth to have plate tectonics. So these other solar system bodies I've been showing you, they have tectonics. You have the crust moving, but when it moves, everything it moves as one continuous crust, everything linked together. Europa may be broken up into plates, and so it's a really exciting place. So let's talk about its place in the Jupiter system. And we have Europa here. You can see the second moon with its sister satellites Io, Europa, Ganymede, Io, Ganymede, and Callisto. Io, these are the 4 Galilean satellites, so named because Galilei discovered them when he trained his telescope on them in such a long time ago. And so Io is the most volcanically active body in the solar system. There are volcanoes going off everywhere. Ganymede is the largest moon in the solar system, and it's the only moon in the solar system to have its own magnetic field, like Earth has its own magnetic field. And then Callisto is a little bit smaller than Ganymede. It has a pockmarked surface. Those are caused by impacts by asteroids and comets and things like that. And so we have on the bottom this tidal energy, and we see that its tidal energy is, you have quite a lot of it when you're near Io, and as you go out to Callisto, it pretty much diminishes. So what is tidal energy, or what is tidal heating? So tidal energy, or tidal heating as I like to call it, is just what happens to these moons as they're orbiting Jupiter. They're much smaller than Jupiter, much smaller. Jupiter is huge compared to Earth, so it's it's gargantuan compared to these moons. And so as these moons are moving in their orbits around Jupiter, different parts of them are pushed and pulled and tugged at different times, and that creates friction. That friction that's caused by that pushing and pulling, it's just like if you rubbed your hands past each other. You start doing that, you keep doing it, your hands get warm. So that friction from Jupiter causes the innards of these bodies to be heated quite a bit. Io gets the most heat because it's closest to Jupiter. Because it gets the most heat, volcanism is the geological process that dominates that surface. We'll skip over Europa, but as we get to Ganymede, you still have tidal energy, not nearly as much as at Io, but you still have some. And so tectonics, movements in the crust and the lithosphere, are what really affect the surface of Ganymede. By the time you get to Callisto, poor Callisto, there's really no tidal energy for Callisto. And so we don't expect Callisto to be a dynamic world. We're looking at it has all these impact craters. If there were things upwelling from the subsurface, such as cryolavas, it would kind of smooth out that surface. We don't see that. But Europa's in an interesting place if we look at Europa. So Europa gets not as much tidal energy as Io, but more than Ganymede. And so it's in a regime where not only can you have tectonics, but you can have volcanism. So this is an exciting thing. And if we talk about Europa's place in the Jupiter system, again, I have just two movies, if they will work. They worked before. Let's try to get out of this and see. Okay, so this first movie just shows Europa orbiting along with Ganymede and Callisto, and Europa orbiting with Ganymede and Io. And Europa, Ganymede, and Io are in a resonance. And just in simple terms, that means that for every 4 times Io orbits Jupiter, Europa orbits twice, Ganymede orbits once. And it's kind of difficult to see here, but this is what this animation is supposed to be showing. And so because Europa is in this kind of resonance with Ganymede and with Io, it's also pushed and pulled and tugged in its orbit with Ganymede and Io, and that adds additional heat to its interior. And this second movie just shows what I'm talking about when I say it's pushed and pulled in different parts of it, or elongated and shortened in its orbit around Jupiter. So that's great. So we've talked about, give me 1 second here. Okay. So, great. And it put me back at the beginning of my talk. How great is that? We'll get there. Okay, and this is right where I need to be. So we've talked about the difference between volcanism and cryovolcanism. We've talked about where we see cryovolcanism. We've talked about Europa. Is there evidence for cryovolcanism on Europa? And the answer is yes, there is. The Galileo spacecraft sent us back lots of nice images. We got a lot of these images back in the late 90s, into 2000. And we see at the top left, you see a pond-like feature. It does not look like the surrounding plains in the back. And so it looks like a pond, therefore planetary scientists, we call that the pond. And it's a smooth feature, and it looks like you've had some sort of runny fluid that's just come up and erupted and flowed onto the surface just in that circular area. And then to the right of that, this mitten-shaped feature, guess what we call that? The mitten. And so the correct name is Murius Chaos, but most people call it the mitten. And so the mitten basically just looks like you've had this kind of viscous, sticky lava that kind of erupted and came out onto the surface and kind of spread and kind of up-domed at the edges. And we think that's what happened there. At the bottom, you have this darker spot on Europa, Thrace macula, to the bottom left. And that's pretty cool. It's much darker than the surrounding terrain. And then beside it, to the right of that on the bottom, we have a close-up of Thrace. And you can see that although it looks like the center has been baked in place, if you look at the edges, there looks like there's been some sort of fluid that's just been moving across the surface. And so these are taken to be evidence of cryovolcanic flows, of lava flows here. And so these are the nice, quiet, quiescent eruptions, don't cause any trouble. What about the explosive cryovolcanism? Yes, there's actually, we have evidence for that. So we have, this is a double ridge here, and you see this arrow pointing to this white arrow at the top pointing to these darker features, and here's a close-up of that to the right. And it's believed that what happened was there was an explosive cryovolcanic eruption, or several along this double ridge, and it threw up particles and water vapor, and they came back to the ground and kind of lined the surface along these ridges. And then at the bottom, you see a picture where at the bottom left, where you see these reddish brown features. Those are thought to be salts that could have come up during an eruption and discolored the surface, salts and CO2 and other things like that, and you see them surrounding these freckles. And you have the same thing on the bottom right image. And so see if I can go through this a little bit quicker. So the interesting thing with terrestrial volcanism versus cryovolcanism is that when we think of lavas moving through Earth's surface or through the up through the surface of Venus or what used to occur on the moon millions and billions of years ago, is that these lavas, as they move up towards the surface, this is a pressure diagram. So pointing down is to the interior of the planet, pointing up is to the surface. As these lavas, or these magmas, excuse me, as they're in the subsurface, move up to the surface, they tend to want to superheat. So they stay very warm, they erupt, and the issue with cryolavas is if you have a watery fluid, or even a watery fluid that may not even be pure water but just has a little bit of salt in it, as it moves to the surface, it's going to want to freeze, and that's an issue. So how do you solve that issue? Well, you can actually solve that issue by adding salt. Adding salt to some of these fluids will help them want to superheat and remain warm as they get to the surface. And that's really good for the case of Europa, because we see evidence of salts on the surface in areas where we believe that the surface has been in contact with some sort of subsurface fluid reservoir. And so this is just a table showing plausible compositions of icy lavas. You can see that a lot of these are just sodium sulfate salts. If you look at hydrohalite, which is down kind of in the middle, that's sodium chloride, .2H2O, that's just hydrated table salt that could be erupting onto the surface of Europa. And we will skip that one. And so this has been pretty great. So we've talked about cryovolcanism. What can we model on Europa? So we believe that there's cryovolcanism on Europa. We have imagery that suggests that that is true. And so if that is the case, remember I talked to you about what we thought was a icy volcanic dome on the surface of Titan and ended up not being one. We also see things that look like icy volcanic domes on the surface of Europa. And the question is, what would be the necessary lava viscosity and composition to form these domes? And you can see at the top here, we have two domes that we believed are cryovolcanic in origin, again from cryolavas coming out, erupting onto the surface, and then they're very viscous, so they're spreading, but they form kind of like a dome shape. And so we've looked at, what I've done with my colleagues is applied some analytical models to see if we can kind of model the formation of these domes. And so here in this next image, you just see several more domes that we believe, have been formed as a result of viscous cryolavas coming onto the surface. And so these domes have heights between 40 and 100 meters. They're 3 to 10 kilometers in diameter. The size of these domes, they're intermediate in size between domes on Earth and Venus, but they are thought to have formed the same way through just having very sticky viscous lava. And their formation was modeled actually in 2003, initially using models that have been applied to domes on Earth and Venus by Sarah Fagents at the University of Hawaii. And we got Sarah on our team and said, can we make these models a little bit more accurate? So I'm about to show you a slide that's a little scary, because there are two equations and a lot of words, and I won't go through these equations, just to say that the one at the top is a differential equation that describes the process that we're looking at. H is going to be the height of the dome. You see that in the top in the numerator. If any of you are students of physics, math, or engineering, you're used to seeing differential equations, so that's wonderful. We have a nice differential equation. The equation right below that is the solution to this differential equation. And using this equation and putting in certain parameters for viscosity of a cryolava, if we put in parameters for viscosity of a cryolava, that tells us something about the composition, or we can infer something about the composition. So this equation gives us height of the dome after it's erupted onto the surface, height of the dome as a function of its distance from the central vent where it initially erupted from, and time. And what can we do? Can we get profiles? We absolutely can from this equation. And these profiles are symmetric. So if we extended this graph, we'd see the exact same four profiles at the exact same heights and places on the left side as we see on the right. So basically these are four profiles. We've looked at these domes and looked at a certain viscosity. And this shows in the red that after 3 years, this final profile, basically we've tracked after this cryolava has erupted, how it moves and spreads across the surface and what the final profile is. we see that the final profile after 3 years is pretty similar to the profiles of these domes that I showed you on this image. So the final profile is about 80 meters high, about 2.5 kilometers in radius. That's great. We love math. We can do math. That's great. But what does that say about planetary science? How does this final profile in the red after 3 years stack up against topography that we got from the Galileo mission? Well, it's consistent with the topography, but not a perfect match, and that's why we call it science. And so if you look at this red box here, I've taken that red box and kind of these kind of turquoise diamonds are the topography from this dome. And so the models are consistent with topography from Europa that we know from the Galileo spacecraft, but we could always do a lot better. And so that's great. We're going to keep doing that. I just received funding to keep modeling these domes and see what their compositions might be, what their viscosities might be. That could tell us a lot about the subsurface structure of Europa, about cryomagma bodies in the subsurface and how they move to the surface. That's very exciting. And so there are a lot of words on this slide, but I will skip to the final bullet and say that when you do theory, which is using math to figure out things in planetary science, you always want to be able to match that to actually observed data. The model is no good if you look at something on Europa and the two don't match. You could be making up anything and nobody's going to trust it as well. They shouldn't. And so we need better imagery of Europa, higher spatial resolution images, so high resolution images, so that we can get better model constraints. And the bad news is I will not get that. That won't happen anytime soon. But the good news is it will happen in 10 to 15 years. So NASA has a mission to Europa that I'm very excited about. I am actually on the science team. I'm on the camera team. We'll make this nice camera. We'll be able to see domes and other images on Europa in this camera. The principal investigator is Dr. Elizabeth Turtle at the Johns Hopkins University Applied Physics Laboratory. And so I'm very excited about that. It's very nice how many people get to do their thesis on a moon they love and then turn around and get to be on a space flight mission. So it's wonderful. So if we can get this next video to play, I may have to get out of this. And they are going to talk about Europa. Here's just a very short video, and you're going to see Dr. Bob Pappalardo from NASA's Jet Propulsion Laboratory is the project scientist on the mission. You'll see Dr. Claudia Alexander, who did a lot of work on the Galileo mission. Unfortunately, we lost her just a couple of months ago, but they're going to talk about why Europa is exciting.
Europa is the most likely...
Europa is the most likely place to find life in our solar system today because we think there's a liquid water ocean beneath its surface. Now we know that on Earth, everywhere that there's water, we find life. So could Europa have the ingredients to support life?
We might be actually looking at a body that is presently alive, presently active, and presently undergoing its geology. There is too much evidence right now lying around on the surface, the red stuff, that suggests that something's going on there. Is that an environment that is habitable for any sort of life form? By golly, we really have got to go back and figure that out.
We have designed the Europa mission to take a spacecraft and its set of instruments all the way from planet Earth to Jupiter.
Previous mission concepts were for a spacecraft that would orbit Europa, but Europa is bathed in radiation from Jupiter. Any mission that goes in the vicinity of Europa is cooked pretty quickly. Instead, we're looking at a mission that will orbit Jupiter, make close flybys of Europa, and then zip out of the high radiation region.
Kind of like when I was a kid, we had the sprinklers, and we didn't want to be too close to the sprinkler head, so we would run in and get a little water and then run back out again.
This allows us to have a mission that's many years long and to collect and transmit lots and lots of data. As Europa orbits Jupiter, it flexes, and we could measure the gravitational change of Europa by encountering Europa at different points in its orbit. On a typical flyby, we would turn on our remote sensing instruments, we would image the surface, we would interrogate the surface with spectroscopy, and we would do the same thing on the way out. And we would essentially rinse and repeat, and do this many, many times until we understand Europa globally. Images from the Hubble Space Telescope tells us that Europa might be erupting plumes of water high into space. If that's true, then we could fly through those plumes with a spacecraft and literally taste it to understand the composition of Europa's interior.
If it does have the ability to harbor life, how does that work exactly? We'll have enough instrumentation to really pinpoint exactly how the mechanisms would work for replenishing the nutrients in a subsurface ocean.
Europa is so important because we want to understand, are we alone in the cosmos? If there's life in Europa, it almost certainly was completely independent from the origin of life on Earth. That would mean the origin of life must be pretty easy throughout the galaxy and beyond.
And so sorry, the sound was not very good on that. But it's very exciting. They show these images of plumes that it would be great if the spacecraft could fly through. Plumes is just another way of saying cryovolcanic geysers. So it's very exciting. And then Dr. Pappalardo mentioned that the Hubble Space Telescope believes that it saw plumes erupting from Europa about, I believe maybe it was last year a paper came out and we were so excited. And so the one thing that, if I could, just the last slide, the one thing that I was hoping that you all would take away, and did it take me back to the beginning? It does, how wonderful. And then will not let me scroll. Okay. So, so the one thing that I want you to take away is that icy moons are important. Icy bodies are important. You have lots of water on these icy bodies as they orbit. You have their planets, like you have Jupiter, imparting lots of heat. The interesting thing about a moon like Europa is that you have an ocean that's up against the rocky mantle or up against the rocky layer. That's exactly what we have on Earth when we have the sea floor. At our sea floor, we have hydrothermal vents. We have different habitats for life. Lots of interesting things. So when you think about these moons are really what we call astrobiologically important. They have water, they have heat, there are nutrients that are needed for life that could be cycled. Anytime you have those three things, that's always exciting, and that's one of the reasons for the Europa mission. So I thank you so much for bearing with me. I will take questions if anyone has them, or comments, whether they have to do with science or me being a scientist, or I saw your hand first. No, there is no possibility of the moon collapsing. That stuff that's going out into space is coming from areas on the south pole of Enceladus. Enceladus is a round body because we have something that called hydrostatic pressure that works with gravity to keep everything clumped together and strong. Once something's circularized, it probably will not collapse. So if you were to think about an asteroid that was maybe like a rubble pile, where everything wasn't, it wouldn't be circular, it wouldn't be spherical, it would be some strange shape, and then you may have to worry about losing too much to space, but that's not going to happen with Enceladus. I'll go just next.
Thank you very much.
Right, okay, and so the question was, in my opinion, what would be a good place to prospect elements and nutrients, and is that what you were saying? For mining
would be economically important to the Earth.
Economically important to the Earth. Well, I will say with a caveat that I love Europa, but the ice shell is 30 kilometers thick. So there would be lots of good nutrients there and lots of things that you can learn. And you always have students in astrobiology courses that want to do a term project and see what it would take to drill through the ice. That's 30 kilometers worth of ice. It's not going to happen. I believe that if we look at Earth's own moon, though, there are lots of resources that could be mined and could be drilled. We think there could be a water cycle on the moon, which we did not know before on Earth's moon. And the Lunar Reconnaissance Orbiter, LRO, is looking at the moon and orbiting it and taking pictures and taking data. And you always have at these LRO meetings, you have several people who actually talk about mining our own moon for resources. So that would be great. That's someplace that's near to us, and someplace that we could easily place people again. And as generations go and we get further into technology and time passes, then maybe we could have a drill that was big enough to get to Europa. I think the first part for Europa, though, was actually sending a spacecraft there. That's the first step, the first thing we want to do. And yes.
Atmospheres or gravity?
Right, that's a very good question. So the question was, how do atmospheres and planets affect the expression of cryovolcanism on some of these moons? And so it affects it quite a lot. So the smaller the body is, the smaller the gravity is, and when you have these geyser-like eruptions, the farther the particles can go up into space, which is why Enceladus actually feeds one of Saturn's rings water, because it's so small and it's easy for those particles to escape. For Europa, Europa is much bigger than Enceladus. Europa is a little bit smaller than our own moon. So you probably would not have geysers that are able to erupt particles as high, because gravity is just going to pull it back down. For the question about atmospheres, remember I mentioned Neptune's moon Triton, which is the only moon in our solar system with an appreciable atmosphere, and it's a thick atmosphere. It's thick and cold, and it's almost as thick if anyone knows anything about Venus. Venus has an atmosphere that's comparable, except for just Venus's hotness in the inner solar system. So the atmospheric pressure is so high that we don't think you're gonna see geysers on a moon like that. You are going to see just lavas that are flowing out quietly and quiescently, and they're probably going to be very, very viscous. But that's a good question. Very good question. Yes, yes, sir. Right. Okay. Okay. So the question is, do I know how deep the ocean is on Europa? Is that what you're asking? So we know that the water and ice layer together is between 100 and 150 kilometers. We think the ice is about 30 kilometers thick. So that leaves anywhere between 70 to 120 kilometers. So that's a lot of water.
Any theory on how that could have developed? How you get a ball of water?
Well, initially, if I give the theory, we'll have to talk about planet formation a little bit. So I will say that initially what we believe happened is that you have this body, and it was probably maybe a little bit warmer, and at some point, as time passed, as it lost more heat, because these bodies start out a little warm, you had it begin to freeze from the top down. And so that's what creates the ice crust. We think, like Earth, when we think about why we have water on Earth, we believe that we had a lot of volatile and water and light species delivery from comets. So initially how it probably got there was that you had very hydrous, water-rich bodies that kind of clumped together to make Europa. Did that answer your question? Kinda. Our ocean is just a sliver, right? Because Europa is as you move out, further out into the solar system, it's easier for there to be light molecules like water and volatiles and things like that. As you move in closer to the sun, it's hotter. And so it's really nice that we have water. I mean, you look at poor Mercury and Venus, and I mean, they're really, really steamy. So we're kind of right in the right place, what we call the Goldilocks zone, not too hot, not too cold. But as you move further out, for different reasons, and we can talk about a little bit more offline, you are able to have more water as you move farther and farther away from the sun, and it's able to, just stay there and not evaporate away. So there was a question here and then one over here. Yes, sir. Okay, so the question was, would cryovolcanism exhibit any phreatic eruptions or mar craters, and would it be different? So the phreatic eruptions, those are the more violent eruptions, correct?
Well, they're basically not above Earth, but just, I mean,
underneath the surface that causes basically a crater, like the UBB craters in Death Valley and the like?
My feeling is that it could. If we're talking about craters that are just beneath the surface, you would need very high resolution images to see that. And I will say too that we're talking about cryovolcanism, and although I'm very, very excited about it, keep in mind that our first look at cryovolcanism was in 1989 with Voyager 2. And if we want to put that into perspective, that was when I was 5 years old. And for science, that is yesterday. That's just yesterday. So it's an emerging field, and I would say that is possible. I would have to think about the physical processes and what would be needed as far as composition and maybe thickness of a regional thickness or thinness of a crust that would allow that to happen, of course. Okay, and yes. And probably one more. Okay, yes, sir. Okay, so the question was, when we think about volcanoes on Earth, they're a little bit more circular, and I showed an image earlier where I said that you probably had cryovolcanism along a linear feature, and what's the deal with that? And so keep in mind, when we think about volcanoes on Earth and volcanism, there are different types. So we see these nice cinder cones, but we also see, if you remember from, let's see, one of the first slides, exactly, the fissure eruption, which is to your left, the bottom left, where you have lava erupting from what looks like a line source. So we believe that we definitely see the same things on Earth that we're saying could be happening on Europa. So it's not that, it's still a volcanic eruption when you see a fissure eruption. It's not as crazy and as out there as it seems. Now, in finding that picture, I may have forgotten a little bit of your question and gotten off, but did I answer that? Okay. All right, that's it. Thank you so much.
This has been a presentation of the Library of Congress. Visit us at loc.gov.